Hello and welcome back to this free training series on FEMA P-154, Rapid Visual Screening of Buildings for Potential Seismic Hazards, brought to you by the Federal Emergency Management Agency's National Earthquake Technical Assistance Program. You're watching Module 5 on Key Building Performance Indicators. So you're watching Module 5 of 9 outlined here. In Module 1, you were introduced to FEMA P-154. Module 2 went over earthquake hazard and seismic performance of buildings. Modules 3 and 4 went through the rapid visual screening procedure itself. This module, Module 5, will go through key building performance indicators. Looking ahead, Module 6 and 7 will go through the FEMA building types. Module 8 will be a class exercise, and Module 9 will be some concluding remarks. With that, Mike, please take us away.
And so Module 5, which is the content of this module, we're going to be looking at key building performance indicators, including building additions, adjacency or pounding, and we're going to start to go into our modifiers, which is associated with our irregularities, both vertical and horizontal irregularities for buildings, and then we're going to talk briefly about non-structural performance. So building additions, this becomes challenging for many buildings, where we have some sketches here of buildings that are reflective of vertical additions. So we can actually have a building that was originally constructed of several floors, and then sometime in the future they've designed and constructed another level or floors above that level. And so we've got vertical additions that we have to deal with. Were they designed with the same type of materials and lateral system, to where when we score them, they're reflective of the building type that we've selected it to be representative of our building. Similarly, we can have buildings that have horizontal additions to them, both as part of the same building or just a adjacent building that is located very closely, and it could have some impact on the seismic performance of our building. And so we refer to that as adjacency. And so for building additions, P-154 procedure addresses how we evaluate adjacency under the level 1 and also level 2 criteria. We don't score this particular evaluation criteria within the RVS level 1 score, but we do note it because it could be potentially hazardous. It becomes one of these other hazards that we record at the bottom of our form in the center. So here's a chart from the P-154 document in terms of our evaluation criteria for building additions. So criterion 1 states, does the building have visible and aligned joints over the entire height of the 2 exterior walls and across the roof? And so what it's saying is, okay, we have 2 buildings side by side. Are there unique joints between the 2 buildings that you can distinguish the buildings are obviously different? That's what we're looking at. And that could be from the architectural style used between the 2 buildings that suggests that they are separate buildings. If they do have visible joints, i.e. separate buildings, then we have to score both buildings separately, and then we evaluate pounding, which we'll get to the pounding criteria here shortly, which represents how close are the buildings relative to how strong the shaking is or seismicity region my building is. If my response to that criteria 1 question is, do I have visible or aligned joints the entire height, then it's no. I go to criterion 2. Criterion 2 is a 3-step process. It says, part A, do I have any abrupt or noticeable differences in the architectural style between the 2 buildings adjacent to each other? And similar to what I was talking about for criterion 1. I can tell that difference is just due to the architectural cladding between the 2. One is brick and one is looks like concrete, for instance. Part B for criteria 2 says, do I have visible differences in the structural framing that I can tell between the two buildings. An example would be I can see a steel frame in one building, and my building I know is concrete. Well, that's two visible different materials framing those buildings, and so they're different, therefore two separate buildings. The third one, or part C in criterion 2, says, do I have differences in the floor heights throughout the elevation? And that really suggests, do I have horizontal mobility between the two buildings, suggesting I have the same building, or if they don't align, more strongly suggesting they're two separate buildings. And so any three of those, A, B, or C, is true, then I have two separate buildings and I evaluate them separately. If not, then I evaluate it as a single building for the whole thing. So that's our adjacency criteria or evaluation criteria. Then we evaluate the building for pounding. And so how we do that is it's a function of our building height as well as our seismicity region. And so we see here in the slide two separate buildings. We have a 6-story building on the right and a 3-story building on the left, with a separation gap between the two adjacent walls. And so pounding is considered when our gap is less than the actual gap between the buildings, and as a function of our story height of the lowest building and our seismicity region. So if our floors are separated vertically by more than 2 feet, this was our criterion 2C, I believe. Well, we don't have horizontal mobility, so our floors do not align, they're separate, right? If the floors are changing elevation between them are more than 2 feet, then we have to apply the gap criteria. If we have one of the buildings 2 stories or taller than our adjacent building, then this criteria applies. We have to apply it. If we have a building that is at the end of a row of buildings of 3 or more, then we have to apply this criteria. The row of buildings is, if you think of smaller rural towns where you've got downtown regions and all the buildings are literally constructed right up against one another for the entire block. And so that's what this criteria suggests, is if you're on the end of that entire block of buildings right up against each other, then we have a concern with that and we evaluate the adjacency issue associated with it. And then we also, as part of the pounding criteria or adjacency, we have to evaluate, well, could falling hazards from the taller building fall onto the shorter building? And so that's how we evaluate that. So here is our pounding criteria for level 1. It says, again, we have our 6-story building and our 2 stories or less building, 3-story building. If we have a separation gap and we're of a 1/2 inch times the number of stories for the shorter building. So in this case, we have a 3-story building is our shorter building. Then 3 times 1/2 is 1.5 inches. That's the separation gap that we have to have between our buildings to satisfy our pounding criteria if we're in low or moderate seismicity region. It increases, the gap does, as we shake the buildings more strongly. So in a moderately high seismicity region, our gap has to be 1 inch times the number of stories in the shorter building. If it's in a high seismicity region, it's 1.5 inches times the number of stories in the shorter building. Again, the gap. And if we're in very high seismicity regions, we have to have 2 inches times the number of stories in the shorter building. And so if you have a 3-story building, 2 times 3 means we have to have a gap of 6 inches between our 2 buildings in terms of satisfying the pounding criteria. If we have less gap than that, then we flag this as a pounding potential on our form, and it's recorded as other hazards. It's not scored again, but we record the fact that we have a small separation gap or adjacency issue. And so this picture here shows a hospital campus and in the Midwest, and where all the buildings are such that they're right up against each other, and there actually is horizontal mobility between each of the building sections. This is the Midwest. It gets cold and snow in the winter, and so no one likes to walk outside. And so when they build a new building adjacent to an existing one, they want to be able to walk from one building to the next all the way throughout the campus. This photograph illustrates that to where you can have a pretty serious pounding problem if moderate or large earthquake shakes this particular site. Here's two examples or photographs of pounding damage. Our photo on the left shows a taller building, just barely can see it on the left hand side, and on the right hand side is a shorter building. And what you're looking at is some cracks at the top of the shorter building as the taller building tries to deflect or displace across the shorter building, which generally is stiffer. And so it's really treating that roof of the shorter building as the ground. And so it's pounding, and cracks are evident in the block that's there at the roof section. The photograph on the right is showing two buildings separated, roughly 3 inches, but the building displacement was significant enough that they actually touched and pounded and caused damage. But what you'll see here is this is a case where our floors do not align. So we do have two separate buildings, but the floor on the building on the right-hand side is impacting a narrower bearing wall for the building on the left. Whereas that floor on the right-hand building is that's our diaphragm floor, horizontal element. That's a very stiff element. But it's hitting a much weaker element on the building adjacent to it rather than at the floor to floor, which will be limited damage, but in between floors to where we have a much less stiff, weaker element, and that's becoming damaged, where we see quite a bit of damage here. And these illustrations are from the New Zealand earthquake in Christchurch in 2011. Let's transition to looking at our vertical and horizontal irregularities, which are our first modifiers that we are to consider for our level 1 scoring. And so if we look at vertical irregularities first, we have a series of them that fall into this category. And in fact, vertical irregularities are noted as either severe, based on building type and the type of vertical irregularity, and whether or it's moderate, so severe or moderate. And honestly, I never remember which is which, and that's where I need to refer constantly back to the P-154 document. And in fact, the P-154 document in Appendix B has a series of our guide that has all of the vertical and horizontal irregularities in pictorial as well as editorial form, so you can quickly glance at it and figure out, oh yeah, I've got a cripple wall failure or a cripple wall vertical irregularity, and I've got a W1 building, and I know that's severe. And so the guides are really helpful in that regard. So back to our first vertical irregularity, and it's a sloping site. And so we're looking here at an illustration of a multi-story building that transitions down a slope. And so we've got our grade elevation on the high side is 2 stories above the step down of the building to the lower portion of the site. And so we have a sloping site. And so the criteria is, if we have a slope greater than 1 story from one side of the building to the other, then we've got a vertical irregularity sloping site. And so we have to account for that. It's severe, and there's 2 scores. There's a severe score and a moderate score. If it's severe, if we have a sloping site for a W1 building type, which is our residential wood frame homes. It's moderate for all other building types. So all other 16 building types, it's a moderate irregularity, vertical irregularity if we have a sloping site associated with our building. The next vertical irregularity is unbraced cripple wall. And we have a pictorial here of a 2-story wood frame home that has a crawl space or elevated first floor underneath it. So there's a crawl space underneath. And this is very typical of home construction in the western portion of the United States. You don't see so much of this in the central US. But it's an unbraced cripple wall. So if we have this condition for our wood frame home, W1 or W1A building types, W1A as a preview is a multi-story wood frame apartment building, if you will, is considered a W1A. If we have this condition as an unbraced cripple wall in our building we're looking at, W1 or W1A, it's considered a moderate vertical irregularity, and that's how we would score it. If we have what we call a short column or pier vertical irregularity, and here we have 2 examples of buildings to where we've got illustration of a building on the right that shows we have some columns and large spandrel beams between the columns framing into it. And on the left, we have another building that shows similar, but we've got wider piers that go up. And in between the piers at the lower level, we've actually bricked in a portion of that where they were between the piers completely empty, just glass, and come along and they've input brick to make a smaller window at the top. This is what we call a short column or pier effect, where we've changed the response of the building potentially as a result of this change. And so if we have this type of condition in our buildings, we have to identify it as a vertical irregularity. And in this case, it's severe, no matter what building type that we have. You're generally going to see this in concrete shear wall or concrete frame buildings to where they do this. So that's a short column or pier effect, vertical irregularity. We could have the next vertical irregularity is a split level. And a split level says, I have a condition to where the building, one portion of the building frames into the mid height of the story of the other section of the building. Now, the issue with this is we know that it's a vulnerability from earthquake after earthquake if it hasn't been designed to resist the forces associated with this difference in elevation between the 2 sections at an intermediate level. We can easily or visually identify this type of condition. That's why it's flagged, and it is a true vulnerability. If we have this condition, split level, then it's a moderate vertical irregularity, and that's how we should score it for our building type, for all building types. If we have our next vertical irregularity is a weak or soft story. So here we have an illustration of 2 sides of a multi-story building, concrete frame building, where at the upper levels from the 2nd floor, up 4 levels, we have very consistent wall sections, piers and columns that flow down the structure to the foundation level. But when they land on the top of the 1st floor, ground floor, we have a lot more openings. So think of garage door openings, etc. A lot more openings at the base of the structure, which makes it weaker in plane in that direction. And so when we see that type of condition, Our forces are accumulated and have to flow to the foundation level, so they're higher at the base of the structure. And so we've weakened the structure as a result. Those aren't two good conditions. Highest forces, weaker section, it could be a potential for building collapse. So we identify those types of conditions, and in this case, it's recorded as a severe vertical irregularity and scored as such, no matter what building type that you have. Similarly, we can have a building that is similar to a split level, but it's not at a frame. The roof doesn't frame into an intermediate floor level. It frames in at the same floor level, but it's a setback. So we have an illustration here of a building which has a 2-story section, and then it steps up higher 3 more stories to the building section, and then the rest of the building is that 5 stories. And so we have a vertical out of plane setback. We can easily see that when we go to the field, and it's been recorded, lessons learned, that this introduces high stress concentrations at the vertical step. And so we can flag it. May have been designed for it, but we don't know. But we still identify it. If we have this condition in our buildings, then we have a severe vertical irregularity, no matter what building type we have. Generally, where we'll see this is when we have load-bearing structural walls in this type of condition. Another vertical irregularity is an in-plane setback. And so this is a condition to where here we have another illustration of our typical building, 5 stories, to where we've got a very large wall section or shear wall section of the building that's coming down on the outside. We can see it much more than we've got windows in the other section. But when we land down on the first floor of the building, it lands on 2 openings with just columns and beams, no shear wall. But to the right of those 2 openings is a nice long shear wall, but it's offset. In plane of the wall, it's offset. Well, our seismic forces, as they travel down the building, what we call our load path, goes down this upper, wider shear wall pier until it lands on these openings. And that load wants to go to the shear wall along that plane, but it's offset. So it has to travel over laterally in plane to that shear wall and then down to the foundation level. Well, that kind of introduces a discontinuity in our load path. And if it hasn't been designed for that, it could be detrimental to the performance of the building. So we identify it. If we have this condition in plane setback, it's a moderate vertical irregularity, and we flag it. Now, here's 2 pictures of examples of vertical irregularity. So on the left, we have a sloping site with a series of wood frame buildings that looks like wood frame buildings are supported on it. And they just step down the hill. It's a pretty steep grade. And so the building's foundation systems just step right down the hill. So we have a sloping site vertical irregularity, and we would score that for each of these buildings. If it's wood frame, then it's going to be severe. If it's, say, steel frame for some of these buildings potential, then it'll be a moderate vertical irregularity. The photograph on the right, I like to call, it's an architect gone wild. This has a series of vertical irregularities associated with this building. We have out of plane setback. We have in plane setbacks. And it's we've got some sections of each of these subsequent floors above cantilevering further out along the edge of one of the walls. And so we have quite a few vertical irregularities here. The point being for this particular building that has multiple vertical irregularities associated with it, it has a severe vertical irregularity. And so that is the only modifier that we would select. So let's say it has It has a severe vertical irregularity and also has a moderate vertical irregularity. We don't score both. We only take the worst condition, which in this case is severe, and that's the only score that we use when we score the building. So it's illustrative of how we account for vertical irregularities. We don't count for all of them at the same time on a level 1 screen. Now, if you were to do a level 2 screen, the design professional that would be doing it does account for all of them at the same time, but the scoring's different. But in a level 1, we just take the most severe. So if it's a severe vertical irregularity, that's the score we use, not both. Here's another good example of soft or weak story photograph. So this is from the Loma Prieta earthquake in 1989 in San Francisco in the Marina District. We have a 4-story wood frame apartment building that the 3 stories above are sitting on top of garages. We call tuck under garages. And so in plane of the garage doors at the first floor, we have a soft or weak story. And the photograph shows that the building is leaning to the left, from the foundation up to the first level above the top of the garages, maybe a foot. So it's pretty close to collapse in this regard. But that's an example of a weak or soft story where we don't have any lateral resistance in plane at the base of the structure due to the garage door openings. A level 2 vertical irregularity, like I mentioned, we have each of the vertical irregularities associated with the building, if it has multiple, are scored. And so we've got that condition in the 2 illustrations here. We have an out of plane setback, both cantilevered out as well as stepped back within the building structure. And so we would account for both of those when we do a level 2 screen for the building, and both of those would be scored. So that's a level 2. Plan irregularities. So let's step into plan irregularities. The first one we'll talk about here is a torsion plan irregularity. Torsion is similar to a weak or soft story, but the weak or soft story is only on one side of the building. And so we see a sketch here of a 3-story brick masonry building, to where we've got the storefront at the first level being all glass, and then the other 3 sides around the building being pretty much solid brick walls with very few openings. So we're creating a condition on one side of the 4 that is weaker at the base of the structure than the other 3 sides. And so when this building is shaken, this side, which has the weaker first story, is going to displace more than the other side in plane of the building due to the more solid walls on that other end. And so what this does is it introduces torsion or twisting in our building as a result of that. And so we flag that and score that as a plan irregularity. Again, that's torsion. We can also have buildings, here showing a photograph of a building with that has non-parallel sides. It's not a rectangle or a box. It actually looks like a triangle with a very small footprint in the nose of the triangle, if you will. We call these non-parallel systems. And so it might have been perfectly designed for earthquakes in this condition where it's not a rectangle or a box, but we don't know. But we can easily visually identify it. We can introduce some problems if it's not designed because of the non-parallel systems. Again, nature loves symmetry. Give me a box or rectangle, it's perfect. But in non-parallel systems, we've got to introduce a little bit more torsional irregularity to the building, and it's got to be designed for it. So this is non-parallel systems. One of our most common plan irregularities is what we call reentrant corners. And so this is a condition where we've got a building Here's a illustration of a building, multi-story, that has one section of it that's attached to a bigger section of the building, but at a 90-degree angle. And similarly, there's another wing 90 degrees to that main section of the building to the left. So we've got a condition where we've got two rancher corners, which is the inside corner of the building. Again, we've got building sections that are of differing lengths relative to their heights, that are going to have differing dynamic characteristics in how they respond to the earthquake, but they're attached at these rancher corner locations. And so that introduces higher stress concentrations at these corners. And that's where, again, it's easily visually identifiable when we're out in the field, and it does cause problems to buildings. We know that. That's why this is a modifier. And so we can easily identify that. Now, we have to have a projection away from a main building of more than 10 feet. This is not your 2-foot bay window on your home does not constitute a rancher corner. It's not sufficient. It needs to be more than 10 feet is the guidance in the P-154 document. But this is probably one of our most common plan irregularities is rancher corners. Architects don't like a square or a box. They got to put wings in it, and that's where we usually get. Another plan irregularity is diaphragm, large diaphragm openings. And so this is a condition to where our roof might have skylights in it, to where we've got in the middle of our diaphragm, our roof, to where we have large openings. And so if the building has been designed to accommodate that, how are we going to transfer forces from our diaphragm level into our vertical elements and down to the foundation? That's the problem. Again, it's visually easily to identify this, and the criteria is if we've got a diaphragm opening that encompasses more than 50% of the width of the diaphragm in either direction, then this is a potential vulnerability, and we need to flag it as a plan irregularity and score it as such. So that's diaphragm opening. The last horizontal plan irregularity is what we call beams do not align with columns. And here's a photograph of a parking garage to where we've got the columns for the building displaced outward from the beams. The beams do not frame into the center lines of the column. They frame into the inside edge of the column with the column displayed outward. Again, it's an architectural type feature, but again, symmetry between the alignment of the beams with the columns potentially introduces high stress concentrations. And so it's again visually identifiable, and we flag it. And so this is a plan irregularity. Beams do not align with columns. So again, plan irregularity, we don't have to worry about the severe or moderate. It's just a plan irregularity. Vertical, we have to worry about the difference between whether it's a severe or moderate irregularity. So here's an example of a plan irregularity. Here's a photograph showing a large multi-story apartment complex that has many wings with a kind of a central corridor that goes through it. But we've got a lot of wings here, and it's right on the water someplace, probably on the ocean. But we've got a lot of reentrant corners. And so again, visually identifiable, one of the most common types we see. It's a plan irregularity, and we score it as such. Here's another 2 examples of plan irregularities. The photograph on the left shows an older downtown building, 2 stories, where we have that open storefront where we can see the sidewall is pretty much void of openings at the first level. And so we can introduce some torsion within this building. So that's a plan irregularity. The photograph on the right shows an interior picture of, it looks like a hotel probably, where we've got the diaphragm cutout. So it's got a nice atrium that goes all the way up the structure at the interior, where we see the floor diaphragms around the exterior perimeter. Again, may have been designed for it, but they're not continuous all the way across, greater than 50%. Therefore, it's a planned irregularity, and we score it as such. So non-structural components. The P-154 document doesn't do great justice for non-structural components. It really only looks in the context of falling hazards or life safety risks. And so when we look at non-structural components, though, it's a function of the ground shaking, which shakes our building structure. And so the more we shake the building, the more we're going to dislodge things, our non-structural components, which is our cladding, could be our ceiling systems, signage, canopies that are on the side of the building, etc. And so we're worried about those types of conditions that if we're looking at doing an RVS screen for a building, whether those could come down in an earthquake. And so we would like to identify those for corrective action. So that's going to be a function of our seismic design and detailing for those. Generally, what you'll find is that non-structural components are not handled by the structural or seismic engineer. They're handled by the architect or the mechanical engineer or the electrical engineer for their particular discipline. And some of the stuff has prescriptive industry standards for high seismic regions. Ceilings are a good example of that. ASTM E580 is a standard, industry standard for how to install ceilings, drop ceilings in high seismic environments for the contractor. So you don't need an engineer for it, just do it like this is pretty much what it is. Exterior falling hazards for non-structural components. Quite a few examples. We have a sketch here of a building, 3-story building. We've got signages, a sign, Acme sign on the side of it. We've got a canopy structure over an egress route. We've got a storage water tank at the top on a frame, which could fail and then fall over the side of the building down below. So we'd want to flag that type of thing. Unbraced chimneys are another great classic example where we see a lot of damage, even in low shaking environments. Parapets, similarly, unreinforced masonry parapets. We could have a building with heavy cladding, and depending on how strongly it's shaken, we can dislodge some of those cladding panels. Heavy veneer is another example. We might dislodge some brick. If we've got brick on the front of our homes, we could dislodge that brick and it could fall off. If it's near an egress route, exit door, we kind of want to flag that. Again, we don't score non-structural component hazards. We flag them for attention later on, but it doesn't affect our score. And we can have other conditions such as appendages on the building, rooftop equipment, or cornices that could possibly fail and fall off the building during strong shaking. So chimneys are a very classic example of non-structural component failures that we like to identify using the 154 procedure. Here's a photograph from the Christchurch earthquake showing looks like a fairly large chunk of masonry chimney above the roof line that has failed, collapsed onto the roof, and now there's just a big hole in the roof. So the masonry chimney, the top, is somewhere inside the building structure. Here's a couple more examples of chimneys where we've got a photograph on the left from the South Napa earthquake in 2014 to where we've got some bricks from a masonry chimney that have failed, and it's a debris pile on the sidewalk below the chimney. The photograph on the right shows a home with a masonry chimney that was attached to the side of the structure, but the chimney has completely failed. And I guess luckily the chimney failed, or most of it failed, to the exterior, and there's a rubble pile down below the actual chimney with some of the masonry sitting on top of a low roof structure that looks like a carport. Parapets are another vulnerable non-structural element, unreinforced masonry parapets that typically fall. Again, like module 2 described in terms of building performance, our displacements are greater at the top of our buildings. And so these are subjected to those higher displacements, and they tend to cause damage to those parapets, which can then fall down on the ground. Here's another example of brick cladding performance. So a wood frame home that's clad with brick, and the brick has pulled off and failed on one side. And you can, from this vantage point in the photograph, you can see the let-in bracing for the home. That's the lateral system. The brick was purely just part of the cladding system and didn't contribute to the overall response. But the connections failed and the brick masonry collapsed out in front. Luckily, this wasn't in front of a exit to the home. We can have appendages that fall. We've got a lot of old churches that are unreinforced masonry that have church spires on top. We have gable ends on a lot of the projections. And so those are subject to higher displacements, and being unreinforced, they're more susceptible to damage and could fail and then fall. So here's a photograph showing a church in Christchurch during the 2011 earthquake. Other examples of appendages. Here's a photograph of kind of a domed spire with a fairly intricate kind of cornice around the base of it, and then a low roof, which actually has a Starbucks sign on it, which says the Starbucks store is in there, but portion of this cornice wall system has failed, and you can't see where it went, but it's conceivable it's probably went through the roof and is inside the Starbucks store now. But again, this is appendages that are susceptible to damage that can fail that we want to capture. Here is a video of some typical interior non-structural components. And this is a video from eDefense over in Japan, one of the largest shake tables in the world. And to put in context here, what you're going to see here is they have modeled the structure to where it's as if you were on the 30th floor of a high-rise building. And so the shaking at that level is going to be, pretty large. You're going to have large displacements for a building at the 30th floor if you shake it. I don't know if many of you have been in a tall building during a windy day. You'll feel it shake. It's the same concept here, except we're shaking it more strongly, and it's displacing more. And so these are typical interior spaces to where the building is shakes, and so we can see and get on a good appreciation of how non-structural components, particularly contents, behave in strong shaking. So I'm going to go ahead and play that here right now. Okay, the main building is starting to shake. Don't look inside or stay focused to the inside. We'll see close-ups of each of the individual areas. Look at the overall building response first. Remember, I said it was large displacements. We're at the 30th floor. And so that's to be expected. And if you look at the building response, does it look violent to you? That's what I'd like you to kind of focus on. It's, sharp shaking back and forth. Or is it just more gentle rocking and kind of rolling back and forth? I think it's the latter. But we'll see what kind of changes that we see to interior contents in these next few clips. So our first space is going to be a typical office type environment where we've got bookcases and shelving and desks. They even put some mannequins in here to give us a little realism. So a big difference in terms of impact from that type of shaking to the building. The non-structural components are damaged. It's very dramatic. That is the killer copier on wheels, by the way. If you thought things on wheels are isolated, they're not. So here's another environment. We got some bookcases. In the forefront here is an exit, a door to the right. So imagine that. Here's contents falling. Now the door is blocked. If we're still can get out from underneath the debris, we still have to move it to get out of the door. There's a fire in the building. You can see how things kind of multiply with this type of damage. Here's a little more cleaner office environment. Now we're starting to see some mitigation for particularly the CPU on the table and one of the laptops, double-sided tape. And actually those contents are actually okay until the killer copier starts to bang on things. So again, think of your environment. Now, notice the bookcase or cabinet on the left, that's been attached to the wall. Our mannequin here does what we're supposed to do after when shaking starts, and that is drop, cover, and hold on. And notice the bookcase. Very simple mitigation can be achieved through brackets to the wall. That keeps everything in place. So much different result with a little bit of mitigation. So here's like a living room environment. There's a cabinet on the left. There's a TV. Someone sitting in a chair. Again, our building motion was not violent, but it translates to a much different environment once we're inside, and that motion starts to shake non-structural components. So here's a bedroom, you're sleeping, and I think most of us can now appreciate what's going to happen. And you can imagine if it was a small shake and it stopped, we'd be okay, but if it gets stronger, we're going to incur greater damage from our non-structural components. So go home tonight, look around your bedrooms, your kids' rooms, and look for these types of things. Here's a kitchen. I'd like you to focus on how quickly you're going to have to make a decision to drop, cover, and hold. And you can see they put contents, mass inside the refrigerator to make it more realistic in terms of its behavior. And this one's great in terms of thinking, you know, drop, cover, and hold on. You got to make a decision fairly quickly, depending on what your environment is that surrounds you. And so I enjoy this video. It's one of the best non-structural videos that I've come across to really kind of bring home non-structural content performance within earthquakes. So I mentioned earlier about the Appendix B reference guides. They're fantastic because it summarizes everything. It has the adjacency criteria in there that we went through in terms of the table I talked about. It has the pounding criteria. It has the vertical irregularity criteria. So here's a snapshot from the guide for vertical irregularity, where we're looking at the different vertical irregularity categories: sloping site or unbraced cripple walls. It shows a pictorial sketch of what is meant by that and whether the severity is moderate or severe, and then a level 1 description of what the criteria is in evaluating that particular vulnerability. Then we have a similar chart for plan irregularities. Again, we've got the plan irregularity identified: torsion, non-parallel, reentrant corner, etc., with a sketch, as well as our textual information about description of that, and then how best to evaluate that particular plan irregularity. There's also in the guides a level 2 reference guide for vertical additions on buildings, a little more rigorous than the level 1, to where a structural engineer can actually take a look and do a little more refinement in terms of how best to address that particular adjacency. So with that, let's have a quick quiz. And our quiz is, which of the following is a vertical irregularity? So vertical irregularity, if you recall the ones we went through, is it a reentrant corner? Is it a diaphragm opening? Is it a soft story? Or is it torsional irregularity? So go ahead and pause your video for a few minutes. Think about that. Which one would you select? And we'll come back with the answer. All right, Gigi, which one do you think it is?
These are all irregularities, but the only vertical irregularity is the soft story irregularity.
That is correct. Soft story. Remember, the soft story is somewhat related to torsional, but torsional is only one side. Soft story is throughout the building on all sides. So with that, do we have time for a few questions?
Yes, definitely. All right. So what is the most common plan irregularity that you've encountered in performing RVS screening reviews?
One of the most common is the re-entrant corner, because architects love non-square rectangular footprints for buildings. So they always have wings. You always have a lot of wings. So you have re-entrant corners. That is one of the most common ones we always see when we do RVS screenings.
I feel like we see a lot of the torsional irregularities if we're downtown and you have a lot of storefronts where you have that open front over and over and over again in a lot of those buildings too.
Yeah, definitely that pops up in that instance.
Great, thank you. All right, so you showed a lot of images of brick masonry chimneys failing. How vulnerable are they?
Very. It doesn't take much of a shake to cause damage to unreinforced brick chimneys. And in fact, the smaller earthquakes that we have out here in the Midwest, you're in the high 3s, low 4s, to where we're seeing damage to those unreinforced brick masonry chimneys and parapets, and versus and unreinforced masonry buildings, whereas all other buildings, even if they haven't been designed for seismic, are doing okay. That's a pretty low level of shaking, but to cause damage to those types of elements suggests that they are very vulnerable.
All right, so in the next module, module 6, Sarah will take you through the FEMA building types, focusing on wood and steel. She'll give you an overview of all the FEMA building types, and then go through wood building types, steel building types, and manufactured housing. This concludes training module 5 on key building performance indicators. We will see you in the next one.